There are two parts for this problem. The first part we will use the method of Frobenius to determine the recursion relation of the coefficients. Then we determine if there is a solution that is decreasing for x greater than 0. We get there when we have the solution. But first, the Frobenius theorem, we will write the series expansion Frobenius method. We're just going to add R to the regular series. Take derivative. And the second derivative. And then we'll substitute that into the original equation. So we have, I just multiply the x squared into the second derivative. So we have x squared second derivative. So we just have the summation n equal to 0, infinity, n plus r minus 1, a sub n, x to the n plus r minus 2. Now if we multiply the x squared into the series, x squared times x to the negative 2, those cancel out. So we just have n plus r. Next, I will multiply the coefficient, and that gives us negative 35x, negative 5x squared, and then the derivative. N plus r a sub n, x to n plus r minus 1. And then plus 324 times the function. I can write it, that doesn't matter. Just keep it outside for now. N equal to 0 to infinity, a to the n, x to the n plus r. Right. The next step, since all of them have x to the r power, we can factor out x to the r power. And then let's just copy everything else. N equal to 0, infinity, n plus r minus 1, a sub n, x to the n, x to the r factor out, so we just have x to the n plus. Actually, now we will minus the negative 35, and we distribute that into the series. So first we have negative the summation n equal to 0, infinity. First we're going to put 35 n plus r a sub n, x to the n plus r minus 1. Of course, we multiply by 35x is 35 in the x with the negative 1 cancel out. X to the first times x to the negative 1 cancel out, and we just have that. And then minus the summation n go to from 0 to infinity, 5 n plus r a sub n, x to the, by the way, we factor out the r, so there's no r here. X to the n and then n minus 1 originally. But notice that we multiply the 5x squared into it. There's a 5. There's the x squared times x to negative 1 will be x to the first. So we change that to n plus 1. Once we multiply the x squared inside, and that's what we have. And then we still have 324. Just bring that inside. 324 a sub n x to the n. Again, x to the r factor out. Right. Next, let's check where the series starts. The first series, when n equal to 0, and it will start at x equal to 0. The next series, n equal to 0, it starts at x equal to 0 as well. The next one, n equal to 0, we have x to n plus 1, so this one starts at x to the first, and the next one will start at x to the 0 power. So the x to the 1 is the higher one, so we're going to keep that, which means we have to split out a bunch of terms. For the first series, we have to write out for n equal to 0, so we will write 0 plus r n is 0 plus r minus 1 a of 0 x to the 0, which is 1. Right. And then next, the series we start from n equal to 1. Everything else stay the same. N plus r minus 1 a sub n x to the n power. The next series, because it starts 0, we have to split out one term. 0 plus r a sub 0 x to the 0, so that we split that term out. And now the series we start from 1. (35) n plus r a sub n x sub n. The series stay the same. Right. The next series start at x to the first power, so that's good. We're going to keep it. Don't need to do anything for that series. N equal to 0 to infinity 5 n plus r a sub n x to n plus 1. That's much good. The last series we have to split because it starts x to 0. So we have 324 a sub 0 x to the 0. And now the series we start at 1. Between 24 a sub n x to the n power. Right, so we're going to group on the part that in black ink. That combined give us the initial equation. That's what I'm looking for. So x to 0 we simplify a lot, so we just have r minus 1 times a naught minus 35 r a naught. X to 0 power is 1 plus 324 a naught. So that part is the initial equation. Everything else, we can write that as x to the power of k. So first one, so this one is x to the n, so pretty much we can match this to x to the k. So n equal to k. Don't need to do anything there. Same thing here. N equal to k. N equal to k. The only thing that need to change is this one. If we say that is x to the k power, so n plus 1 is equal to k. So n is equal to k minus 1. Right, now we change the series in terms of k. Right, the first one, all we need to do is n equal to k, so we write k instead of 1. And we have k plus r minus 1, a sub k, x to the k power. The next series, k instead of n, 35, k plus r, a sub k, x to the k. Next series, that need to change. N equal to 0, n is k minus 1, so k minus 1 equal to 0, so k equal to 1. And 5, n is k minus 1, so k minus 1 times k minus 1 plus r. Minus 1 is n plus r. N is k minus 1, x to the k. And the last series, change n to k. That's what we have. Right. Now, since the right-hand side is equal to 0, all the coefficient has to be equal to 0. So the first part is, this part has to be equal to 0. And the second part is all the coefficient combined, that has to be equal to 0. So we have two things here. The first part is, I just factor out a naught. So we have a naught, r squared minus r minus 35r plus 324. That has to be equal to 0. A naught is, we can divide a naught on both sides, so we will have the equation r squared minus 36r plus 324 equal to 0. And we have the double root of r equal to 18. So r equal to 18. The second part, if we factor out x to the k and combine the fraction, we should have, now because all the series start from 1 to infinity, so we just wrap that, factor out x to the k. So pretty much we just have k plus 1, k plus r minus 1, a to the k, x to the k, factor out, minus 35, k plus r, a to the k, x to the k is factor out, minus 5, k minus 1 plus r, a to the k minus 1, and plus 3 and 24, a to the k. And that coefficient has to be equal to 0. So pretty much we have this, multiply x to the k, when we combine the series, and all of this has to be equal to 0, so the inside, the bracket has to be equal to 0. Now we focus on two things. First, r is equal to 18. We're going to put that into the second part of the equation. and then we combine. So again, R equal to 18. So the part inside the bracket, now we focus on to this part inside this bracket will be K is K and R is sorry, this is K plus R. K plus R. Okay. R is 18, so K plus 18. R is 18 minus 1 is 17, so K plus 17. A sub K minus 35. K plus 17. I mean K is 18 actually. Minus 5. K is 18, so 17 plus R. R is 18, so K plus 17. A to K minus 1 plus 324. A sub K equal to 0. I will continue on next page. Right. Pretty much just multiply them out and combine like terms. So for A to the K, we have K plus 18 times K plus 17. Let's see what do we have inside. Now if we have all of them have A to the K, now focus on that and factor it out. We have K plus 18 times K plus 17 minus 35 times K plus 18 plus 324. So K plus 18, K plus 17 minus 35, K plus 18 plus 324. And then the part that has K minus 1, we just have minus 5. K plus 17, a K minus 1. That has to be equal to 0. Now we simplify inside. A sub K, K squared plus 35K. 17 times 18 is 306. Minus 35K. And 35 times 18 is 630 plus 324. And now we'll move the 5 and K plus 17 on the other side. K minus 1. Right. I simplify inside the parentheses here. We have A sub K. Right, let's look at the numbers. 35K minus 35K. 306 and 324, that is 630. Actually cancel with everything. So we just have K squared, actually turned out to be just K squared A sub K, and we have 5K. 5 times 17 is 85. A sub K minus 1. So from this we have the recursion of A sub K equal to 5K plus 85 over K squared A of K minus 1. Right, so that is the recursion from the Frobenius, the method of Frobenius. Now, let's analyze the solution. Note that our solution is going to be equal to y equal to x to the k, a0 plus a1x, a2x squared, and then so on. Note that all of the coefficient, if we choose a not to be something, then the coefficient here, let's say if a k, we should write here a few things. If we start with a positive coefficient, then on the index, because of this recursion, this part is positive, so we always have on the positive coefficient. So on the positive coefficient when multiplied by x. So let's say if x is positive as well, then we have to base on that. Now, if x is all of the x are positive and all the coefficient is positive as well, what we see here is when the bigger values of x, the bigger values of y. The bigger the x values, the bigger the y values. So which means this is y is monotonic increasing, or just say increasing. Because we have coefficient being positive, the x is positive, the bigger the x, the bigger the values, because the coefficient is positive. Right. The question asks us, do we have anything that is decreasing? And if we want decreasing, then we have to turn things around and we say x is still positive though. If we start with a negative solution. Now, if we start with the negative here, and then the coefficient will be negative. In that case, everything will reverse. If we start with the, let's say with the negative, and then we multiply something to it positive, and then so on, the coefficient will be negative for every k. In that case, when x is increasing, when x is bigger value for x, the y values will go down. So y is decreasing. That is only if we choose a not less than 0. If a not less than 0. So we just like, I'll give you a simple example. So we have something, again, all the coefficients are positive. Let's say 2x plus 5x squared plus 7x cubed. Let's say something like that. All the coefficients are positive, and the bigger values for x, the bigger value for y, that is increasing. Now, if we turn everything to negative, then this function is decreasing. Pretty much, if we take the derivative, and then when we change the sign of everything, we go from increasing to decreasing. So in this case, it is decreasing if the a naught less than 0. Only if a naught is less than 0, then it is decreasing, given that x has to be positive. And that's what we have. Let me zoom out and see the whole problem. To standard Frobenius method. So we rewrite everything, the series. Now we're just going to add the r to it for the Frobenius method, and then we find derivative, second derivative, substitute into the function, and then simplify. So we should have the two parts. When we factor out x to the r, there will be two parts. One part is the initial equation that is outside of the series, and then all the series inside, where we can combine the series and give us one series. By the way, we can factor out x to the k along with x to the r, and all the coefficient equal to 0. In this case, what we have is a relation where we solve for the relation. This is the relation we have a of k in terms of a of k minus 1. Notice that the 5k plus 85 over k squared, that is always positive. So if we start with a positive a naught, everything will be positive. If we start with the negative a naught, everything will be negative. Now, and the rest, we just look at the simple example. Like if y equal to 2x, the bigger the x, the bigger the y, so that is increasing. If we throw in the negative, the bigger the x, the smaller values for y, so that is decreasing. So in this case, we do have a decreasing solution if we choose the a naught less than 0. And that, of course, only works if x is greater than 0.